Thank you everybody for being here. And I would also like to thank the organizers for inviting me to give this presentation. So the title of the presentation is Multi-Agent Model-Based Control Methods for Urban Traffic Networks. And this is actually joint work with some of my PhDs and postdocs, including Andreas Hedji, Rudy Negenborn, Shulin, Solomon Zegeye, and Lakshmi Bhaskar. So this is the overview of the presentation. So first of all, I will give some background on a control method called model predictive control, which is actually a model-based, optimization-based control approach. And I will explain how it can be applied for traffic networks. We will see that there are some issues, especially if we are going to look at large-scale traffic networks. And that's why I will discuss three methods to deal with those issues. The first method involves the proper choice of traffic models. Then we will go to distributed MPC or equivalent multi-agent MPC. And finally, we will discuss multi-level multi-agent MPC. And we will conclude with a summary. So first of all, some basic background. So the idea of doing traffic management is, of course, to reduce congestion, emissions, noise, and so on. And this can be done in various ways. And the setting that we include here is that we consider a traditional setting. So where we still have roadside control measures. As we will see at the end of the presentation, the approach we propose here is actually generic and can also be used if we go to more autonomous or self-driving systems. So the idea is that we apply control measures such as traffic signals, variable speed limits, ramp metering, and so on to steer the traffic. In addition, we can also include soft control measures like the one that you see here. And we might say that if you want to reach the airport, if you go to the left, there's a traffic jam of 3 kilometers. If you go to the right, there's a traffic jam of 2 kilometers. And we even have included this type of control measures. Of course, you have to be very careful with those, because if you manipulate them too much, you might lose your credibility with the road users. And as we will see later on, the approach we use allows to deal with several performance criteria, including total time spent, total travel time, fuel consumption, and so on. And we will mostly kind of capture all of them together by considering a weighted sum of the different performance criteria. Then the control approach that we apply or propose is the so-called model predictive control approach. Actually, it's a method that already exists for a long time, both in process control, where it was very popular since the 60s, and actually some of the earliest control approaches that have been used in the traffic field for traffic signal control are actually a special type of model predictive control. So how does it work? First of all, we define a performance criterion, and we will denote it in the remainder of the presentation by capital J. And then the system, of the control approach works as follows. We have here a system, in our case, that will be our traffic network. And we first measure the states of the system. That will, for example, be the queue lengths at the traffic signals or the speeds of the vehicles inside the links of the urban network. With the measurements, we are going to run an optimization. The optimization considers some performance criterion, but it can also include constraints, for example, on the queue lengths. And then we use a combination of a model to predict the future behavior of the system, and we apply an optimization module that will then determine the optimal control actions. And here we use a model-based optimization. So we run this model inside the optimization loop. Then after a while, we have obtained a local optimum, or we have to finish our optimization because it's time to output a new control action. These control actions are then fed back to the traffic system. And then after a while, the whole process is repeated. This repetition kind of allows us to introduce feedback, and that has a very positive influence on disturbances or disturbance rejection. So by regularly measuring the current state of the system and re-optimizing, we can also be adaptive towards changes in the system. And also we can deal with small mismatches between the system and the model. So in general, this will lead to a so-called nonlinear optimization problem. So we are going to determine the future control inputs. We look NP steps ahead. NP is the prediction horizon. And we are, for example, going to determine for maybe 5 or 10 minutes in advance what would be, for example, the optimal cycle times, the optimal split rates for the green traffic lights, and so on. We collect them for each cycle in a vector U, and then we are going to optimize for the next 5 cycles, and that's then collected in the bold U. And we then use our optimization to determine the optimal settings for the control measures. So that's MPC in a nutshell. On the next slide, I will explain the receding horizon principle. So the idea is that at the current time step K, we are going to determine some optimal control inputs. In general, we have to look over a certain prediction horizon, but if the prediction horizon becomes too large, we will have a lot of different values that we have to optimize. And to reduce the computational complexity, we typically also consider a control horizon. And after the control horizon has been reached, we keep our control inputs constant. In that way, we can reduce the number of variables in the optimization problem. And the advantage is that typically the effect of these faraway control inputs will be much less than the control inputs in the near future. So we compute the optimal control input sequence over the horizon, and then we will apply the first value to the system. And at step K plus 1, we are going to repeat the whole procedure. So here we measure again the state of the system, and then we shift everything. So instead of optimizing from K to K plus NP, we will then optimize from K plus 1 to K plus NP plus 1. And that's every time we optimize over NP values, and that's called the receding horizon approach. Okay, so if we then look at large-scale traffic networks, we immediately come to the main issue for MPC in practice, and that is that we have to solve, in general, a nonlinear, non-convex optimization problem, and that is an NP-hard problem. So in practice, this will lead to a huge computation time, and that's why we have to find or to come up with methods to address this computation time. And there are many solutions in the literature, and some of them we will discuss here. So the first involves the choice of the prediction model. As explained in this figure, the model will be executed a lot of times because it's part of the inner optimization loop. And whenever the optimization generates a new iteration point, we have to evaluate the performance. So we have to run our model. Hence, it's very important that we have a very fast model. But then the trade-off between accuracy and computational complexity comes into view. And we will have to find a model that is on the one hand fast enough, and on the other hand also still accurate enough. And that will be discussed later on in the presentation. The next step is to not compute all the control inputs over the entire prediction horizon, but do it in a smart way. And one way to do that is to use a controller with parameters in them, and then to optimize the parameters. And finally, we can also use a distributed or a multi-agent approach. And if the network is really big, we might even need a multi-level approach. So the first three approaches or solutions will be discussed in the presentation. Alternative approaches involve to select the right optimization approach or the right optimization algorithm. For example, there are some methods that allow to use analytic gradients, and they have been shown to perform quite well for MPC for traffic networks. We can also use distributed optimization, or we can approximate the original problem by another problem that can be solved more efficiently. And actually, we will also see a few examples of that later on. And then the final solution involves including application-specific knowledge of your particular network. So let's now move to the first option, and that is the choice of the prediction model. In general, if you look at traffic models, there are several main classes of traffic models. And one way to divide them is to make a distinction between microscopic models, where you are going to follow individual vehicles, and macroscopic models, which consider aggregated variables. So in microscopic traffic flow models, for which you see here a screenshot of a simulator, Paramix, there you're going to track individual vehicles and you describe how vehicles follow their predecessor, how they may change lane, and how they may overtake another vehicle. In addition, these models also allow to model or to consider different driver classes with different parameters for the drivers. The advantage of these models is that they are quite well for simulation and for visualization of your traffic network, also to validate your model. But if you want to use them for optimization, they are too slow. And so they are less suited as a prediction or as an optimization model for model-based predictive control. And that is why we can consider so-called macroscopic traffic flow models, where we do not work with individual vehicles, but we work with aggregated variables. For example, the average speed in a link, or the density, the average number of vehicles, the flow, and so on. And in urban traffic context, there are several models in the literature, such as the store and forward model, the cell transmission model, or the S model. And later on in the presentation, I will briefly consider the S model, but it will just serve as an example. If you want to apply another model, then the whole approach of MPC will still work. And it's important that we then get a trade-off between the computation speed and the accuracy. These models typically are very fast and they are sufficiently accurate to be used in MPC. Of course, if you want to do a detailed simulation or a detailed validation, they are not the best choice. But we will use them as prediction model for our MPC controller. Okay, so we are going to use this model, the S model, as an illustration, but we can also use other models if we want. So how does the S model work? It's actually a discretized model both in space and in time. The temporal discretization is quite rough, so we consider one cycle time as one time step. And in general, we can also actually consider different cycle times per intersection. So every intersection can have a different cycle time. That's allowed. And there are two main state variables, the number of vehicles in the links and also the queue lengths at the end of the links. And in the next slide, I will just give the main impression of that model. So in general, if we consider a link that goes from an intersection U to an intersection D, then the number of vehicles will be updated as the previous number of vehicles plus the inflow minus the outflow. We also assume that inside the link here, the traffic or the vehicles are just driving, and close to the intersection, they kind of prepare themselves in queues. So we have here a queue for left, a queue for going through, and a queue for right. We then have to make it or to derive an expression for the delay that vehicles have between entering the link and arriving at the tail of the queue. And therefore, we have an expression which actually takes the storage space length. So that's actually the number of vehicles that are in the link up to the beginning of the queues, and we divide it by the free flow speed or the speed in the traffic link. That gives us a certain delay. Since we have to map that delay to an integer, we work with the floor and the remainder, and we take actually an average between the floor time step and the previous time step. So it's actually kind of weighted average where we round the actual travel time to the nearest cycle, and we take the remainder into account to add the weight to the closest value. So this describes the delay between entering the link and arriving at the beginning of the queues. Then the queue lengths are updated by the queue length plus the arrival in the queue and the traffic that leaves. And finally, the vehicles that leave, they are actually the minimum of three values. One is determined by the intersection capacity, so the saturated flow rate. We also look at the vehicles arriving at intersections, so actually the vehicles that are in the queue. And we also see whether the downstream link is blocked or not. So if there's no more space for vehicles in the downstream link, we also take that into account. And then we take the minimum of the three values. We also need some additional equations to map one intersection to another, because we have one cycle time per intersection. That also means that we have a different cycle counter per intersection. There might also be an offset. So we also need an interface between those intersections. That goes quite deep, so I will not go into detail here. But the idea is that with some linear operations, we can actually recast the flow rates of the expressed in the timing of one intersection into that of the timing of another intersection, and that's how we can interface two intersections. In general, this leads to a nonlinear non-convex optimization problem, but since by using some tricks from piecewise affine modeling, actually, if you look at the model, you will see that if we take an average storage space, then the delays becomes constant, and we get actually linear equation here, a linear equation here. This also is a linear equation, and a minimum expression is actually a piecewise affine function. And using some properties of piecewise affine function, we can then actually translate our problem as a mixed integer linear programming problem, for which there are efficient solvers available. And to show you the advantage of actually approximating your original problem using another problem, that you can actually get a high speed up. So that's the example of one of the solutions that I said before. You can approximate your original problem by a more simple problem and then gain a huge speed up. So in our case, the main approximation is that we assume that the delays are constant. So as an example, we consider a grid with 4 intersections. We have a simulation model. This is also a model comparable to the S model, but the sample step is 1 second. So it's much more accurate than the S model. So here are some additional data. And for the nonlinear optimization, we use 5 starting points. So let's now look at the results. So what you see here is the total time spent. That's what we are going to optimize. You see here 2 nonlinear non-convex optimization algorithms. On the one hand, we use the gradient-based sequential quadratic programming and also a pattern search method. And then here you see the mixed integer linear programming approximation. Actually, there are 2 variants. SMLP is the one that I briefly explained, but you can make some additional approximations and then you get the so-called S star. But we are going to focus now on this SMLP. So if you look at the effect of using the approximation, you actually see that in this case, the approximate solution is better than the original solution. And that's because for the nonlinear non-convex optimization, we could only use 5 starting points. So we have a local optimum, but not necessarily the global optimum. So we see that actually the performance is comparable, but if you look at the computation time, then we see that for the nonlinear optimization, we typically need like 600 seconds of CPU time to compute the solution for 5 starting points. Or in the case of pattern search, it's even much higher. Whereas for the MLP approaches, we are roughly between 3 and 2 seconds. So we get a huge speed up by using this approximation, while we see that the performance is quite similar. Okay, so this is then the first main solution to deal with the computational complexity, is to select the right simulation model, and if possible, even approximate your original optimization problem by a simpler one. However, this will not always work. And that's why we now propose a second solution to deal with the computational complexity, and that is parameterized MPC. How does it work? In general, if you're going to use MPC, you're going to optimize all the control inputs. For example, in an urban traffic network, you would optimize the cycle times and the offsets and maybe the green splits for all the intersections in your network. And that can become a huge optimization problem. So the number of components of U can become very large. And that's why we're going to do something else. We are going to parameterize U. So we are going to write U as a function of some parameters theta and the state of your system. So we measure the queues, the queue lengths, and the speeds inside the network. And with some pre-described control law, we then determine the control inputs. And in that way, we can actually get a new problem because now we have to optimize the parameters of the control law instead of the U. In general, this will mean that we lose some optimality because with this control law, we cannot always retrieve the truly optimal control solution. But since the parameter theta can be much smaller than the original U, we can have a large speed up in computation time. In general, we will have a speed of up to 80% while we still have a comparable performance. So here you see the scheme then. It's a bit more complex. So we have again our system that we want to control. So our traffic system, we do the measurements and we have a control law. But now we're going to use MPC to optimize the parameters of the control law. So this is then the MPC controller block. It duplicates the control law, and we use optimization in combination with a model to determine the optimal values of the control parameters. They are applied to the control law, and then the control law uses the measurements to determine the control inputs. An additional advantage is that we can now work with two speeds. For example, this loop could be done in a fast way. Maybe we update it every second or every 10 seconds. While the optimization loop, we could take a slower frequency, so we can take more time to optimize the parameters and in that way get a better optimum. So here you then see the main difference between the MPC, which is indicated here in blue. You can directly optimize it, or you can optimize parameters of a control law. The parameters can either also vary over time, but less frequently, or you can even keep them constant. If you do that, you can still have your control input vary at every time step because you're going to use the control or the state of your system to determine the input. So even if the parameters are constant, your control input can still be time dependent because the states of your system will also evolve over time. Okay. So in general, this leads to a huge speed up while still giving the same performance. Now, to give a flavor of how this control law could look like, I give two examples here. And now we are moving actually to the freeway context, but you can do something similar for urban traffic signal control. So here you see, for example, how we can determine the speed limit as a certain parameter multiplied with the free flow speed, plus another parameter times the speed difference between two consecutive sections and the density difference between two consecutive sections. And the idea is that if the speeds and the densities are the same, you don't change your parameter, your speed limit a lot. But suppose that you either get a huge speed drop or a huge density drop, that means that you have to slow down your traffic and you will need to adapt your value of your speed limit according to the speed drop or the density drop. And these are then three parameters. And actually we can use the same parameters not only for one intersection or for one segment of the traffic network, but in many segments. So in that way, we can actually reduce the optimization problem significantly by only optimizing a limited number of parameters. Okay. So I will now go on to a case study. We applied this approach for a highway in the Netherlands with two objectives. On the one hand, minimizing the total time spent and also minimizing the total emissions. And what you see here is, let's first look at the first column. So if we optimize the total time spent, then with regular MPC, we get a lower function, a lower value, because normally we are more rich. But if you use parameterized MPC, we get a comparable value for the optimal total time spent. So we see roughly like 20% improvement compared to the uncontrolled case. But the CPU time needed for parameterized MPC is much lower than the one for the regular MPC. If you look at the emissions, we see a similar picture. So uncontrolled case, these are the emissions, 219, and it drops to the range of 80, 90 for parameterized and regular MPC, while parameterized MPC is much faster here. Again, here, the fact that regular MPC performs less well than parameterized MPC is just because we could not find the total overall optimum because we needed too much starting points. So parameterized MPC is also an excellent way to deal with the computational complexity of the MPC problem. And this one I'm going to skip. However, if you have a very big system, then still with those two tricks, parameterized MPC and using an appropriate model, you will not get there. So there are more alternatives needed. Sorry. And one of them is to use distributed MPC. So the idea is that you divide your network, indicated here by this grid, into several subnetworks, and for each subnetwork, you define a separate control agent. Normally, the networks are now smaller, so inside every network, you have less variables than in the global network, and you can still run MPC. And then the whole idea is that the different control agents, they have, of course, to coordinate their actions, because otherwise you might get undesired effects. Suppose that the blue agent has locally a problem, and the yellow and the red agents still send extra traffic towards the direction of the blue agent, you get problems. So we need some mechanism to get coordination. And actually, what is essential here is the inputs and the outputs between the agents, so the interconnections. For this, we have a model here described in the following way. For every agent, so the next state is a function of the current state, the local control inputs, then some local disturbances. This could, for example, be the prediction of the inflow, and then the variables that come from the other agent. And this could, for example, be the outflow of the blue agent becomes the inflow of the green agent. So in general, the state depends on local variables and variables that are provided by the neighboring agent. And what we are now going to do is we're going to find a way to make sure that the outflow that the blue agent produces will match with the green inflow that the green agent expects. So we actually need to make sure that even though these agents are optimizing locally, that the interconnections give matching values. So essentially what we need to do is what goes into agent I should equal the outflow of agent J. So we need to get these interconnecting constraints. However, we cannot impose them directly because then we get coupled optimization problems, and that creates issues when we want to solve them for every individual agent. So what we're going to do is we're going to assume some initial values. The agent optimizes locally and then compares the initial values of the inflow with the outflow of the other agent. And we are going to make sure that these values will converge. This will be done via negotiations and a so-called multiple iteration scheme. So what is going on? Essentially, we consider a local optimization problem. That's, for example, the local total time spent or the local emissions. with an interconnecting term that describes the interaction with the neighbors, and I will explain in a minute how this looks like. And then we consider the local dynamics and also the local initial states, disturbances, and additional constraints. So what is indicated here in black is entirely local, and the only interactions with the neighboring agents are in this term. In general, we use a so-called augmented Lagrangian and block coordinate ascent approach, where you're going to make sure that you get a match between the output and the input variables. And we will do this in an iterative way. So what we're going to do is we're going to introduce an iteration scheme where S is the iteration index. And we take previous values from the previous iteration. So these are values that are exchanged at every iteration between all the agents. So these values are communicated, and then they are included in the interaction cost function. But since we take values that we know from the other agents, we now have no more coupling directly between the variables of two agents. We always use the previous value that was communicated by the other agent, and then we optimize. And these terms here, so the difference between the current outflow and the inflow that we expect from the other agent in the previous step, and also the reverse, the inflow that we generate to the other agent and the outflow that we predict, we are going to try by this norm to make them match and to make sure that in the end, the inflow equals the outflow. And this term actually has a similar effect. And then we have an iteration process over S. So I'm going to illustrate this using an example. So suppose that in the initial iteration, we have two agents, and agent 2 expects the red inflow, while agent 1 creates the blue outflow. And actually, we have to make sure that these two match. So in the first iteration, we still have a big difference between the two. But if we iterate, they already move closer together. So the initial inflow of agent 2 was this. It moves down. And the outflow that agent 1 will generate moves up. And if you then go on and you iterate, you see that gradually the difference between the inflow and the outflow will go to 0. And that's then the effect of the negotiation scheme. There are still some issues with this mechanism. Convergence is an issue. Convergence speed is also an issue. Also, if you terminate in a finite number of iterations, and if you have hard constraints, which is usually not the case for traffic networks, you might get some infeasible solutions. And also the extension to the nonlinear non-convex is actually a hot topic and a topic of ongoing research. And there are many approaches currently being developed. Actually, one of the most well-known and most successful is the so-called ADMM, alternating direction method of multipliers. But there are also some methods that use agent-based coordination and consensus, game-based methods, swarm intelligence, and so on. So these methods to get coordination between the different agents is a very ongoing topic, a very active ongoing topic of research. Okay, so now we move on to the last solution to deal with computational complexity, and that is, if it's really too big to handle even with a distributed approach, you may need to go to so-called multi-level approach. This works as follows. So in black, you see here a representation of our network, and we have already defined local control agents. But instead of letting all the control agents interact and negotiate with each other, we define so-called supervisors. So some agents are grouped for one supervisor, and other agents are grouped for another supervisor. And the supervisor actually will now interfere whenever the agents are not able to reach agreement. So we now get a division both in space, but also in time, because typically the control agents will act at a fast time scale and the supervisor will only interfere at a slower time scale. We can also represent this as follows. So what you see here is at the bottom, the local control agents, which are controlling parts of the network. A group of control agents is managed by a supervisor. And if you have a very large system, you might even have a higher level supervisor and so on. At the bottom of the control hierarchy, we typically control the fast dynamics in a small area, which means that the MPC problem is still tractable. If we go up in the control hierarchy, we typically are going to consider larger areas and slower dynamics, especially if we then also approximate the dynamics, we still get a tractable problem because we have more time to solve it. What is the main issue now? That we need coordination at and across all levels, and MPC can actually help us with that. And I will illustrate this for a control scheme, where at the bottom level we have, for example, individual traffic signal controllers for each intersection. A group of intersections may then be controlled by a so-called corridor controller. If we go up, we might get an area controller, regional controller, and so on. We can even use this to combine urban traffic control and freeway traffic control, because of course the both systems, they also interact. So in general, we then get the following scheme. So at the bottom level, at the lowest control level, we have control agents that actually need to act very quickly. So typically, we would then use some very fast logic, learning-based AI approaches, PID controllers, so very fast basic controllers. If we go up a bit in the hierarchy, we have a bit more time to do the control. So at the top level, you would typically be working in the second level, and that's too fast for MPC. But at the corridor and the freeway stretch level, you would typically have like a minute or even 5 minutes to compute your control signals. So then you can apply MPC. They will typically coordinate the different lower level controllers by providing set points. If we then go up in the hierarchy, we will typically look also at routing. So how much traffic are we going to route from one area or from one region to the other? And how do we control the flows at the interfaces? By looking at larger areas and at a slower time scale, with possibly a simplified model, we typically can still control the size of our optimization problems. And that means that they are still tractable. So we can still run the optimization and find solutions in time. And what I will now do is I'm going to focus in particular on the region controllers. So in general, the region controller has to manage a collection of areas and determine how much flow is allowed from one area to the other. And the model that we're going to use here is the aggregate model, so-called macroscopic fundamental diagram. And that's actually very similar to the model that was used in the previous presentation. In general, we will see that this leads to a nonlinear non-convex optimization problem, but again, we can use some approximation and end up with a mixed integer linear programming problem. How does it work? So the macroscopic fundamental diagram describes for a large area of a city, typically up to 10 square kilometers, the relation between the density, so the number of vehicles inside the area, and the flow in the network. This has been developed by Hieronymus and Daganzo, and the idea is that you typically get this type of shape. In the beginning, you have a free flow. At one moment, you get saturation, and then you go to a congested situation in which the flow inside your network decreases. And we also know that the outflow of the area is proportional to this Q, the space mean flow inside the area. And now we can come up with a model. I will only present it at a very high level. So we are going to define a graph where the links correspond to areas with a certain inflow and outflow and a density, and the nodes will describe the connection between areas. The outflow of an area can be described by the macroscopic fundamental diagram. Moreover, we have a simple conservation law to describe the densities inside the network. So the new density is the old density plus a term which is proportional to the inflow minus the outflow. Moreover, at the nodes, we have a balance between the inflows and the outflows. And finally, we also have a cost function. We can look at two cost functions. We can either consider a penalty in such a way that we can keep the density below the critical density. So this gives this max expression. If the density is higher than the critical density, we get a penalty. But if the actual density is lower than the critical density, this value becomes zero. So then we don't get any penalty at all. So this expression penalizes whenever we are getting above the critical density. The second term, or the second criterion, will penalize the total time spent by all the vehicles in the region. And we can use a weighted combination. So in general, because of this max here, and also because of the shape of the microscopic fundamental diagram, we get a nonlinear non-convex optimization problem. But we can approximate it. First of all, the macroscopic fundamental diagram, we can approximate it by a piecewise affine function. Moreover, if we look at the other equations, so if we describe this by a piecewise affine function, we see that this is a linear equation. This is also a linear equation. This objective function is actually piecewise affine, and this one is linear. So in the end, we get piecewise affine equations, and there are some methods to deter or to translate that into a mixed integer optimization problem. So in the end, we can get a mixed integer optimization problem, and as we have seen before, that can be solved much more rapidly than the original problem. And then we can either use the solution of the mixed integer linear programming directly, or we can use it as a good initial starting point for the original optimization problem. And then we don't need to apply a multi-start solution anymore. Okay. We can also extend this approach not only to use the conventional traffic control measures like traffic signals and speed limits, but the same approach can also be used in the future multimodal cooperative vehicle infrastructure systems, where you have autonomous vehicles that can interact or communicate with each other and with the control center. So what I did in this presentation is I gave an overview of the work done at the Delft Center for Systems and Control on model-based predictive control for large-scale urban traffic networks. And I highlighted the main issue, which is computational complexity. And I proposed several ways to deal with these computational issues. First of all, to come up with a trade-off between accuracy and efficiency, either by using appropriate models or by using some simplifications. We can also use parameterized controllers or use multi-agent or multi-level control. In our ongoing work, we are actually now integrating this MPC, the model predictive control, with learning-based control approaches in such a way that we can combine the advantages of optimization-based control, which is actually optimality and the inclusion of constraints, with learning-based control, which is the very high online computation speed. And if you want to know more about the ongoing and the past work, you can find more information on this website. Thank you for your attention.